Okay, so now what I've done is I've constructed some circles. These are called concentric circles. And I made them so that they're, I'll tell you how I made this guy. Well, let me go back and I'll show you. Okay, I'll go undo all of this. I started by constructing a circle with a radius of 1. Then I dilated that circle with a scale factor of 2. And you can see it says here, circle C prime is circle C, but dilated with a factor 2 from point A. And that means it's the dilation, of 2. When this had a radius of 1, means this new radius is going to be 2. And I continued that for 3, 4, and so then I ended up with 1, 2, 3, 4 circles, concentric. This one has a radius of 1, radius of 2, radius of 3, and radius of 4. And then I constructed perpendicular lines. This one was parallel to the y-axis. This was parallel to the x-axis. So they met at point A and they form 90-degree angles, right? They form 90-degree angles. And then what I did was I marked all the points of intersection for those. Okay? And basically, I went into my calculator now and I made a little table. Let me see if I can get that there. I made a little table where what I've got is my radius is listed here. I've got a radii of 1, 2, 3, and 4. And now I'm going to measure my arc length. Now remember my radian measure. Let's go back and look at that graphic. Remember that a radius of 1 means that 2 pi r, the circumference of this entire circle, 2 pi r, when the radius is 1, so the radius or the circumference would be 2 pi. And if I indeed measured, let's measure the length around the circle, measurement, distance and length of the circle, we see that the circumference is 6.28, which is 2 times pi. Okay? And of course, each one of these then, if I measured each of these circles, this is gonna double because it is a radius of 2. So this is going to be 12.57, and this one's going to be factored by 3. So 3 times 2 times pi, or 6 pi. And here we have 4 times 2 times pi, right? So 8 pi. That's 8 times pi. Basically, that's our circumference. But the radius is 1. Then here's 2, 3, and 4. So now let's measure. We can take off those circumference measurements. Remember that we said, the full circumference is 2 pi. Half of the circumference would be pi. And a quarter would be pi over 2, right? Half of pi. This is half of pi. That's 1 pi. This would be 1.5 pi. And this would be 2 full pi, right? So this is half of pi, or pi over 2 should be this measurement. So we're going to measure this arc. That's arc D, and we get 1.57. And I'm going to put that in here. 1.57 is my measurement of the arc length. I wrote up here, this is arc length, okay? No spaces because the calculator's funny that way. Now let's go back here. Let us measure our next arc length, E. And E came in at 3.14. 3.14. Hey, that looks a lot like pi. Okay. And then we measure this arc length. F is 4.71. And finally, arc G is 6.28. Okay, that's when the radius was 4. Then we have that measurement. Okay, so now what we're going to do is we're going to actually, let's take a look at this really quick. Let's do a little, well, let's see, hold on. We're going to, let's do this. Let's insert a page, and we'll make it a data and statistics page. And let's put down here on this axis, on this axis let's put the radius, and on that axis, so now we just see the radius being marked out. There's 1, 2, 3, and 4. Over here let's put our arc length, and there is our arc length. Pretty interesting. You have a linear relationship. That means a constant that as the radius gets bigger, the arc length is getting bigger. Right? Constant relationship there. So now let's just analyze that relationship a little bit. Let's do a regression and have it show us the slope. So here we have, if we has an intercept of 0, if we have 0 radius, then we'll have a 0 arc length. That makes sense. And then this number here is the important number. This is the ratio by which it's growing, which is 1.57. Now that happens to be half of pi, right? Or half of what we're using is pi right now with our rounding, 3.14. So in other words, every time we add another, from 1 radius to 2 radius, we're going up 1.57, from 1.57 up to 3.14, etc. 4.71, 6.28. Okay, so that's an important thing to see that there's a constant. Doesn't matter how. If I were to dilate that radius, here's 1, but if I were to dilate it any interval in between, it doesn't matter how big the radius is, it's going to stay true to that constant. This is a visualization of that constancy that we were talking about before, that proportionality. How once we dilate, the ratio between arc length and radius stays constant. And it is related by 1.57 arc length per 1 radius. Okay? So 1.57 over 1, that is the ratio right there. And that, of course, is for our angle that we created, which was a 90-degree angle. So this is the basic concept of radian measure. Now we're going to do some calculation. So what we're saying is that, this radian measure can be written as whatever measure, let me write this out like this, whatever measure the angle has over 360 degrees is going to be multiplied by 2 pi. Okay? So this represents the portion, again, of the circle in degrees, and this represents the length around the circle in degrees, and this, of course, is just for a radian of 1, a radius of 1. And then we recognize that this radian measure that we calculate here, we can actually use it to find the length of that arc, the actual arc length, by multiplying by whatever the radius is. If the radius is 6, if the radius is 1/3, we just take whatever its radian measure is of that angle and multiply by the radius, and we'll have the length of the arc. See how nice radians are? Radian measure is very helpful, okay? But it's a little bit goofy. We're not used to it. We're used to 360 degrees. So we kind of want to practice a little bit, okay? This is the formula, okay? M over 360 times 2 times pi. And you can see that can be simplified to M times pi over 180. So now, let's define our radian. I'll do radian as being equal to that. Okay, and you see where that came from. We're taking the measure of the angle over 360 multiplying by 2 pi, and then that would give us a radian measure, right? And we would just multiply it by whatever the radius is, and we'd get the length of the arc. Okay, so now let's try defining M. So what if we had, again, let's have a 360 degree angle. So M equals 360. And then when we do radian, we want to calculate the radian measure there. We get 2 pi. But what about when M is equal to 180? Well, then its radian measure is equal to pi. Hey, is this kind of nice how I put that formula in, called it radian. Now my calculator knows that whenever I type the word radian, it can just run that formula and calculate it for me. All I have to do is put in what the measure of the angle is that I want to calculate it for. So if I want to have a 90-degree angle, then I can calculate its radian as pi over 2. Okay? So that's how we would do that. Let's try another one. Let's try a 60-degree angle. So we go 60, 60, and its radian will be pi over 3. Well, that makes sense. If I drew a semicircle, right? A semicircle is pi units around. 2 pi is all the way around, right? So pi units around is halfway around. That's 180 degrees. And 60 is a third of 180 degrees. All right? How about, well, let's go with 45 degrees. 45 degrees. And calculate that in radian measurement. Pi over 4. Pi over 4. Now that makes sense because remember, all the way around a semicircle is 180 degrees. That's equal to 1 pi. A 90 degrees was equal to half pi. Right? It's halfway around a semicircle is half pi. And then of course 45 is half of that, or a quarter of the way around the semicircle. So pi over 4, or 1/4 pi. So that's how we do those types of calculations. Now we've seen how we can calculate, when given degrees, we can calculate a radian, and we've seen how we can take the radian and we can calculate a length of an arc, of its related arc, by just taking this radian measure and multiplying it by the radius, whatever the radius is, and that'll give us the length of the arc. In a moment here, we're going to watch another video where we're going to talk about the area of a triangle and the area of a sector.